Well, hello, everyone. My name is Joan Baucells. I'm here because I'm the representative of our Institute of Microelectronics in Barcelona in the SustainableNano network that's organizing this series of talks. And today, as you know, we have David Quirion talking on the sustainability on clean rooms. And I will make a short introduction of him. David Quirion was born in Nantes in France in 1974, and he received an engineering degree in physical engineering in 1997, and then a PhD in physics in 2001 from different institutions in Grenoble, France. And the PhD was on proximity effects in superconducting structures. Then in 2001, he went to the Max Planck Institute for Solid State Research as a postdoc to investigate the Kondo effect in quantum dots. In 2004, he joined Canberra, France, as a project leader in germanium coaxial detectors for gamma rays. And finally, in 2009, he moved to the Institute of Microelectronics of Barcelona, where he was in charge of technology development for silicon radiation detectors in the clean room facility. And in September 2021, he started being the head of the facility itself. And as he says, during all these years, he has worked in clean rooms, first inside as a user and now mostly outside as a manager. So, David, when you want.
Okay, so I will share the screen. So thank you, Joan, for the introduction. And so yes, today I want to talk to you about clean room and sustainability. The title is, yes, trying to reconcile the irreconcilables. Yeah, what you can think of clean room, we'll see it at first is definitely not something you think as sustainable. So here, what I want to do very modestly is to give you some thoughts how we could make such a mid-sized research clean room as we have here at the Institute of Microelectronics of Barcelona, let's say a little less unsustainable, or to participate to our great efforts we all have to do to make our world more sustainable. So for this, so the outline of my talk, I will first introduce you our institute here in Barcelona, the Institute of Microelectronics. Then I will give you a very, very short introduction to sustainability, just to place the frame. And then I will explain you what the relationship between clean rooms and sustainability, especially explaining what the clean rooms are and what it implies. And after, at the end, I will show you what we did in our clean room here in terms of sustainability. So let's start. So the Institute of Microelectronics of Barcelona is located at the outskirts of Barcelona on the campus of the Autonomous University of Barcelona. Okay, we are devoted to nano and macro technologies, and our main laboratory is a clean room. You can read here our mission. We are really R&D research, R&D center, because we really do research, but also development, going from really basic research to products. And this thanks to the clean room. To achieve these goals, we are organized in 3 thematic axes and 1 technology unit. And so those 3, I will take a pointer. I forgot to put it. Sorry. Well, there's no pointer, but okay. Sorry. So we have the 3 thematic axes are the health and environment, physics, frontiers, and civil security, energy, mobility, which is here the one which is more related to sustainability. And here, as our director said, we develop solutions to reduce the environmental impact of third parties. So that's really the goal. And these are the 3 thematic axes, and the technology unit, which is the link between the investigation and the research and the clean room, and it's dedicated to develop the technologies, because here we really have the technology. So we have different technology. We can really we do not do only processes. We make devices on established technologies. And here you have the list of the technology where we can make we have very old resilient CMOS technology. We make radiation sensors in silicon and silicon carbide, power devices, ISFETs, memory stores, but also things more related to MEMS activities, such as microfluidics or gas sensor based on membranes, energy harvester. But we also study or investigate very more advanced topics like 2D functional materials or printed electronics. So this gives us a wide range of applications, and here you have, just in a nutshell, everything we do. We can fabricate devices to investigate properties, physical properties of cells, and so we can fabricate devices, small chips, which will be put into the cells to study the properties during the life cycle. But we can also fabricate neural probes, sweat patches in paper. We were an essential infrastructure during the COVID pandemic, and we developed some COVID test platforms. We develop also smart power modules, but and also devices in silicon, for example, for the CERN in Geneva to study the ultimate elementary particles, but also silicon carbide diodes for space missions. So we have such a wide range of the devices we fabricate here in the clean room, from the cells to the sun. So this is very, very fascinating to work in this environment. And all this is possible thanks to the clean room. Okay, so the clean room facility, which is here, you can see it in the picture, and its associated laboratories. But the clean room, which is 1,500 square meters, with the service zone to achieve the ambient conditions we need for the clean room, and we have a smaller clean room for packaging. So the clean room, very short terms, it's an ISO 57. I will explain what it means, and with temperature all the year of 21 degrees and 45 relative humidity. And we work in 2 shifts from 8 to 8. But we are not alone, obviously. We are in various networks. First of all, the Spanish networks of clean rooms, which is Micronafab, with the ISOM in Madrid and the NTC in Valencia. We are also parts of the Nano Labs infrastructures with more than 14 clean rooms all over Europe. And we are also part of the INFFA activity, just to propose some services. So again, more numbers about our clean rooms. So we have more than 150 tools. We are a staff of 45 people, which includes associated laboratories, maintenance, people in process. So the people really performing process are around 20-25 people in the clean room, divided in 13 process areas. You have the list here. And for the year 2023, we made more than 12,000 single steps, which are organized in runs, what we call runs, which is the step sequence to fabricate a device, more than 1,000 of them. And we process more than 4,000 wafers. This is what we would call fabrication we do on our own, but also we have external access, so people, researchers, students can come and work in our clean room. So we had almost more than 1,800 external accesses, single accesses, for a total of more than 3,600 hours. So, but these are the typical numbers we give, but maybe today I want to focus on different numbers. The numbers I want to talk today, which are related, is you have just 2 of them here, is our electricity consumption, which is 6 gigawatt watt hours per year, which is equivalent of a small Spanish city of 5,000 inhabitants. And we have a water consumption of more than 4,500 cubic meters per year, which is well, which is not that much in this case. It's equivalent to 80 people in Spain. But the first numbers maybe is the one which makes my point, or the title of my talk. Is this really sustainable? If we really mid-sized research clean room consume so much electricity? So that makes a question of the sustainability of such an infrastructure. So now that we are talking about sustainability, so let me introduce you sustainability. So there's two definitions, well, there are several. The first one I like is from the German philosopher Hans Jonas, which just I read, acts so that the effects of your action are compatible with the permanence of general human life. And the second one, which is maybe the most famous one, is from the Brundtland Report from the United Nations in 1987, which is about sustainable development. Is a development that meets the needs of the present without compromising the ability of future generations to meet our needs. So sustainability is obviously up to date. We talk a lot about it, even if you can see from those quotes that the topic is already there for more than 50 years. The awareness is nothing prevalent in all the society, but still and you can see it because of for example, the United Nations launched the Sustainable Development Goals. In Spain, we have the Spanish Circular Spain 2030 to promote the circular economy and Spanish industry. More closest to us is the Tenerife Declaration from last year, from September last year, on the global dimension and sustainability of research infrastructures, and even closest to us, well, in the CSIC and in our institute, we have sustainability committees. But what do we want by sustainability, and what do we want when we talk about manufacturing, which is what we do in a certain sense in our clean room? Well, the best one is what is called here the type 3 ecology, is a circular economy. So you just have an input energy. Obviously, it will be renewable energy like the sunlight or the wind or whatever. And from this, well, your whole industrial and societal ecosystem can work. Obviously, we are far from this, and now maybe there is a certain conscience of that we have limited resources, so we have to generate limited waste, but we should be as circular as possible. But unfortunately, for years and years, we thought that we had unlimited resources. We could do the Earth was exploitable and endlessly, and we could generate as many waste as we wanted. And this is a type 1 ecology here in this graphic, and that's something we should definitely end. Okay, so to understand it better, so I just extended this sequence. So basically what we do when we make any manufacturing is we start with some resources, natural resources, oil, gas, whatever, or metals, and from this we extract materials, make something of it. From those materials we fabricate by a product which is sold and used by your consumer, by people, and then we generate waste as limited as possible. So potting, just to explain the way to a more circular economy, those in 2017 just proposed the concept of the 9 R's. We'll explain this now. I call it the 1+9 because the first one we do is just to manage the waste. That's something we are really used to it. So, but now we will go from the less circular to the more circular, from high circularity, which is from the low circularity, which has a higher numbers, to the high circularity with lower one. So the first thing we could do, and we already do, is to recover. That means from this waste, to burn them and to generate energy from it, just to be able to extract or fabricate again a new product. This is still not very circular, obviously. So more circular is to try to recycle those waste and to make basic materials to fabricate new products. To go in further, we can take those products we just throw out And we can or take parts of it and to build a new product of it, which is to repurpose, or we can try to remanufacture them. Okay. Manufacture is we will use it for the same goal, repurpose for a different goal. But still we can do better, and we already do better. You can repair them, or we can refurbish, okay, those tools, those products, whatever. Or you can reuse them. And going more and more circle, maybe we should reduce our use of the resources, because the resources are limited. And even better, we can rethink the whole thing and try to do better, or even to refuse, which is really important. We may say no, which is what he calls what's the R0, which is even out of the bias. So now, so I was starting about clean rooms, so I explain you what is sustainability. So what is a clean room? Just to make things clear, just take the ISO standards definition. The clean room is a room within which the number concentration of airborne particles is controlled and classified, and which is designed, constructed, and operated in a manner to control the introduction, generation, and retention of particles inside the room. Well done. So how does it work? So you have here a scheme of a clean room. So we take air from the outside. It is filtered several times, with several filters, 3, 4, 5, depending. And the humidity of the air is reduced or added, depending on the humidity of the external atmosphere. And the temperature is controlled to the condition which is needed inside. Okay. One of the key elements for a clean room are the HEPA or ULPA filters, which means a high efficiency particulate air, or the ultra low particulate air, which are the filters which are just on the ceiling of the rooms. Okay, of the clean room. So the final filters with efficiency high above 99%. Okay. Maybe to understand why clean room, where do they come from? Maybe a short history is nice. I mean, the first concept of clean working is given by a historian about the Waltham Watch Company in Massachusetts, United States of America, where they try to fabricate watches in the workplace in Roxbury, but they were not able to it because of the dust coming from the street. You can imagine there was not paved, so people, horses, and so on moving in around, and well, it makes production impossible. So they decided to move from Waltham, which was a very rural zone, and there was no dust, and they saw the yield improved a lot. Well, the example is from the mid-19th century, and is American because basically the historian, you have the two quotes here, are American. So if the story maybe told maybe in Europe and maybe from Switzerland, high in the mountains, we can make very nice Swiss watch. But still there was already preoccupation on this. And as much of the technology in the 20th century, the World War II was key. Okay, so maybe the first example we have from the northern bomb sight. The bomb sight is a system. You have a photo here. It's just to target to a place where you want to launch a bomb. Okay, so the northern bomb sight system was a system for the US Air Force. It was used on Nagasaki and Hiroshima in 1945. And for this, they needed very small ball bearings. And so they asked it for a company, and this miniature MPB, miniature precision bearings, and they discovered that dust was very, very key. So they started to think, and doing almost 20 years, because the first order was just the beginning of World War II, they end up with the concept of white rooms. So people in France or in Spain will understand where our words white room comes from. And but it was based mainly on cleaning a lot, and trying not to avoid dust, but mainly cleaning. Also key was the Manhattan Project, for which the HEPA filters were developed, even if the technology came from the gas mask, German gas mask from the First World War I. And this was to protect the workers from the particulate, the radioactive particulate generated in some part of the buildings. And in the first clean room for production was actually done by AT&T for some tubes, vacuum tubes for transatlantic phone cable. As you can imagine, when you put a cable below the ocean, you need a very high reliability. They needed that for more than 20 years to be there without any defect. So, and also cleaning was, the clean conditions were very key. But who introduced the modern concept of clean room is Willis Whitfield in the Sandia National Laboratory. Okay, and he introduced two very key concepts, which is unidirectional ventilation, which is sometimes called equivocally as a laminar flow, which is not laminar because some turbulent local turbulence are accepted, and the safe cleaning room. That means that, yeah, most of the work before was done, yes, the cleanliness was obtained just cleaning. But now you have a room which is, because of the airflow, which is able to maintain itself more or less cleaning. Well, you still have to clean, but much less. Okay, so it's a safe cleaning concept. And what I want to say here is that the clean room are really important for the 20th century, which is a century of miniaturization. Okay, miniaturization means that we need a very precise manufacturing and very precise tools. Just to say, there's a convention, very close parallel story in medicines, and which can be told, but if you read those two very nice articles, you will see it much clearer. So yes, so obviously we have a clean room because we fabricate very small devices. That's what I said, miniaturization, which is a key, one of the keys of the technology in the 20th century. Here on the left-hand side, you have a human hair compared to a transistor for the 90s. Our transistors today are very much smaller. So imagine the disaster it comes when any dust comes on it and you cannot fabricate it. Just to give you some numbers, so where do those particles come from? Well, they obviously come from outside. In the room where you are sitting just right now, where you may have more than millions of particles per cubic meters. Small particles, half a micron, which is one of the standards to measure it. But also anything generates particles, equipments, machinery, processes. Okay, and we obviously, as human, as a living organism, we generate dust particles from the skin. You can see the numbers here: 100,000 dust particles per minute, and also bacteria and whatever. So for this, when just after conceiving the first clean rooms, it became obvious that we need some standards. We have to be able to say how clean a clean room is. So that was a goal. There's a long story of standard, but the final one we have now is the ISO 14645. Just I use it to give you the definition of a clean room before. So it divides the quality of the air depending on the maximum allowable concentration of particle of certain size per cubic meters. And so you have different ISO 1 to 8. And now it's metric. It's based on the 0.1 microns, number of 0.1 microns particles. So the ISO 1, you should have less than 10 0.1 micron particles per cubic meters. But for people like me, maybe we are here in the business for a longer time, we're much used to the first definition when everything was measured in cubic foot, and knowing the conversion value here. So the ISO 3, we used to say it's class 1. So it means that you have less one particle of less than of 1.5 microns per cubic foot. Well, and what do we do here in those clean room? In our case, because we are in a micro-nanofabrication facility, we fabricate devices. And to do this, well, you have this cycle, typical cycle of microfabrication. We add some material, we deposit it, we define exactly the patterns we want to have with the photolithography. Then we move, we etch, and then we check and so on, and you do it 1 time, 10 times, 100 times, and you end up with a device you want to do. So in 2 words, what we have risk of contamination, but obviously to make very small patterns, we need precision tools and products, chemicals, resist, and so on, whatever. And more precisely, which conditions do we need as a clean room? Well, most of it is defined by the lithography. Okay. Temperature. Well, temperature should be, it's advised to be between 18 degrees and 23 degrees with variation of 1 or 2 degrees. And the high temperature reduces the viscosity of the resist and could affect the resist film thickness. It also affects the radiation of the positive resist, and this could affect the development time and resist profile. So if you want to have a repeatability, you really need to control the temperature, but you also need to control the humidity, the relative humidity between 45 and 55%, which is because if you have a higher humidity, well, there will be a layer of water, humidity on the wafer substrate and wafer surface, sorry, and it will affect the resist adhesion. And also, if we have too low humidity, well, it prevents the radiation after soft bake and reduce the development time and rate and so on and so on. So you really have to control both. So that's the conditions we need. But what does it imply? Well, it implies, I just explained you, we need a very advanced heating, ventilation, and air conditioning system to achieve those conditions. And this needs a lot of electricity, obviously. So maybe the best example to get an idea of what it means is to go to the semiconductor industry and taking numbers from what is the up-to-date fab in Taiwan, TSMC or equivalent, with working on 300 millimeters wafers. They consume 400 gigawatt watts per hour per year, which is equivalent of a Spanish city of more than 300,000 people. Okay, and power consumption wise, it depends a lot on the facility, but let's say very briefly that the tools use 50% more or less of the electricity because they're working 24 hours a day, which is very different from here, obviously. And the facility, which means the heating, ventilation, and air conditioning systems, the other half. So you have different papers. I just quote one here to giving you the repetition of the electricity use. But that's not the end of the story. I told you that we need also chemicals, metals, and so on. So you have this very nice paper from Williams in 2002, which said that to fabricate a microchip with a weight of 2 grams, what you really need is 1.7 kilograms of materials, fossil fuel mainly, but also chemicals. And well, it's summarized in this sentence. So the environmental weight of semiconductors far exceeds their small size. This intensity of use is orders of magnitude larger than that of traditional goods. Could be discussed or not, but I think it really summarized well the issue. There's electricity, there's also all the products. So we really definitely have here an activity which is very intensive in energy, water, and materials. We don't have the use of waters here, but it's also much exceeding. In our case, it's not that much as you saw before, but for semiconductor manufacturer fab, it's huge. But that's not the end. Let's have a look on research labs, and you have this initiative in France, Labo 1.5, which is very interesting, and they in this paper, which is still is not published, so maybe we have to look at it carefully, but still the point is most of us are really concerned about our trips, our travels, traveling by the plane and so on. But that's not the end of the story. I mean, in this paper, they really saw that purchase dominates the carbon footprint of research laboratories. It's depending on the activity, obviously. If you're doing maybe humanities, not that much, but in science and technology, the purchase dominate. They accounted for more than 50% of the emissions. And science and technology, especially the laboratory instruments, and you can imagine in a clean room. Wow, it definitely has an impact. So we have to need a strategy in purchase also to think about it, to think the whole picture. So coming back to the numbers of the clean room, we still have the typical activity numbers, the activity also in the electricity consumption and water consumption, but I will also now try to focus on the chemicals, the gases, the plastics, everything we can imagine. So going in details now, what we did here in our clean room in terms of sustainability. So most important one, let's start with electricity consumption. So here you have again the ambient conditions in our clean room, which is ISO 5.7, I already told you, 21 degrees, warrior, 40–50% humidity, which is exactly the condition for the lithography explained before. We have an overpressure to avoid the dust from coming outside, and when an elevation air flow rate or air change per hour between 50 and 150, depending on the quality of the ISO quality. Okay, so I told you before, we have an electricity consumption of 6 gigawatt per year, and this definitely, as you can see on the right, depends on the conditions outside. Definitely, the summer is not a good time for us because we consume a lot of electricity just to maintain the temperature, but also humidity in Barcelona is high. And you can see a peak here in October. That's an example for 2017. We have a very humid October month in which gave us, well, induced a very high electricity consumption that month. But what did we do to minimize or at least control the electricity consumption here? So that's something, an activity we started more than 10 years ago, because first the clean room, which was built in 1991, was extended from 1,000 square meters to 1,500 square meters in 2009. Okay, so this induced an increase, obviously, of around 36% of electricity consumption, definitely. And so we just after that, seeing that the electricity consumption was too high, we made in 2011 a first action. We decided to reduce the conditions during the night, because in the weekend we are not working, so we don't really need to maintain exactly the humidity, and we can relax slightly the temperature. So, and this induced a saving of around 20%. In 2019, we installed some variable speed drives, which help us to control the velocity of the fans, air fans, during the day and the night, and this induced again a saving of around 13%. And so we are now consuming in a 1,500 square meters clean room as much as when the clean room was only 1,000 square meters. Okay. We may extend soon with the CHIP Act. That's still to be seen, but we have to take more actions, obviously, to maintain the electricity consumption, which would be ideal to maintain as it is now. But you can see that 2023, we see that we consume a little more electricity, and this is definitely due to an increase in activity. We have a lot more work now, which is good news. But the chillers are aging, and the climate change is also affecting us, because it's definitely here in Barcelona, the temperatures are higher than, let's say, only 5 years before, at least for 2023. So we didn't stay with inactive for this. So the government in Spain asked for us in March from last year an energy report, and they really define what we could do and what are the savings expected. And definitely what we should do is to replace the 3 cooling machines, the chillers, and we have to upgrade our air conditioners and to install some heat recovery units. That's definitely the 2 actions we have to do, and which could help us to save around 20% of consumption. Okay, this represents quite a huge investment, from between 1 and 2 million euros, but with the CHIP Act or the Spanish CHIP Act, the PERTE money, we decided not to buy less tools, but to focus us on the infrastructures and to invest money here because it's key. Okay. But still, one last point on electrical consumption, which is definitely the major impact or the on environment because of the high consumption. Here you have again those numbers of the ISO with the particle, novel particle, but you have also the average velocity and the air changes per hour. Okay. Well, in California, in 2010, they made a benchmark of various clean room here. You have a summary here in this paper, I quote just here, and they made very interesting conclusions. They just look at the air changes per hour, which is definitely one of the main consumption of electricity, one cause or main source of consumption. And they saw that looking at many ISO 5 clean rooms, they needed less air changes per hour, as is normally recommended in typical table you can find in most textbooks, which is a surprise because then that means that those clean rooms are able to be ISO 5, but consuming much less electricity, which is something that everybody should look and think about it. And really some advice is if you have to build a new clean room, you have to include obviously efficiency in the design, but do not oversize your clean room. That's obvious, but each clean room is unique. You need a system analysis. You have to think about it, and maybe you can consume less. For example, changing the air changing per hour, diminishing it a lot, and you still have a good air quality and improving efficiency. That's the point of this article, and you can read it. And it's possible. Obviously, you already see we did it here. We were able by add day and night regimes and so on to decrease electricity consumption. But they also manage it here in that's the molecular foundry in Berkeley. So they were able to save 35% of electricity just by applying those kind of things I just explained, and changing the electricity suppliers. They were able to finally reduce by 85% the CO2 emissions. Okay, so we can really do it. So next, the water consumption. Maybe I'll try to go a little faster. We consume as not that much here, but still, why do we not use that much water? Because we have three using water in our clean rooms, that's the chiller and the process cooling water, but those are closed circuits, so it's no big issue. Where we use water and we have a lot of loss is for the ultra pure water or the DI water due to the osmosis mainly. We already reuse part of this water for the humidifiers, for the humidifier of the air conditioners, and for the toilets also. But still, we want to do better. And next, in the future, we'll try to recover part of the water which are used in the rinser and dryer and more. So we had a very critical drought here in Catalonia, which seems we are at the end, but still we have to use as less water as possible. Just that's our social responsibility. But okay, I told you there's not only electricity and water, so let's look at all the other elements which have some environmental impact. The gases. We use around 20 gases every day here, okay, for the reactive ion etching, for CVDs, for furnaces and so on. First thing, but very important, all those gases and also the chemicals products are very high purity. So they are very intensive to produce, energy intensive due to purification. It's a lot. So that's the first point. Second, what do we do with those gases? We install scrubber systems for the gas abatement just to avoid sending into the atmosphere toxic elements. We still miss the abatement system for fluorinated gases. We should include it in the future investments. But just focusing on maybe the most famous one, you know that semiconductor industry and all our micro and nanofabrication processes are really dependent on greenhouse gases. Okay, well, you have a list here, a typical list, and they are used mainly in dry etching and CVD and so on. Actually, elements was a compound which the highest global warming potential is sulfur hexafluoride, SFS6, with a factor of 24,000. So can we do? Well, to be honest, it's very hard. I think as a research institute, we should try to contribute to this. But in the microtechnology industry has been trying for years and years. They improved a lot, but still, well, I just quote one of the last one using a gas mix of difluoride, argon, and nitrogen, if I'm not wrong, to substitute the carbon tetrafluoride for CVD chamber cleaning. But still, there's a lot of work to be done here. Chemical products. Well, what I said about the gases is true here. They are high purity, so they're very energy intensive to produce. So we definitely have to reduce their use or to use them as exactly what we need. Here in our cleanroom, we have more than 50 references of chemical products, different products we use. We can have in our warehouse more than 3,000 liters of chemical products. And we use also a lot of resins and developer for photolithography. What do we do? Well, we have a seed neutralization plant here at house, and for all the other chemical waste, where we have an intermediate storage until recycling. But maybe there's other ways. Well, you have here two papers try to substitute resins for more environment friendly compounds like silk for EBL, e-beam lithography, or maybe for deep UV here in one case, which is a collaboration with French group with Zeletti, based on chitosan. Okay. And about cleanings and etching, maybe first start with important things. The semiconductor, the microelectronic industry for years has reduced the concentration of processing chemicals to reduce cost, obviously, and environmental impact. In our case, we decided we use mainly wet benches with 5 or 10 liters each. So anytime you need to make a cleaning, you need to have, for example, 5 liters of piranha. Obviously, we optimize and use it as much as possible. We try to purchase a new spray tools. We purchase it. We are still waiting for it for cleaning and to switch from wet benches to spray. We generate a lot of waste. When you start to go into details, it's a huge bottle from chemical products, all the gloves and the face mask, all the filters for the air conditioning system, we change every 3 months or every 6 months or every years or every 7 years, depending on the filters. So lots of them. We have a very strong waste management. We had for years a manual for waste management in the center, and depending on the type of waste, so we have different recycling. I think that's a common, but it's worth to mention it because at all stage we should do it. And what we are doing now, which is maybe the key for sustainability, is to make really a flow analysis of our activity. So we have a master thesis ongoing by Guillermo Cito, studying our metabolism and life cycle assessment of our clean room. So he analyzed everything which comes in, electricity, water, gases, materials, metals, chemicals, gloves, face masks, and so on, looking at what goes out from this. Obviously, we produce devices, but plastic waste, emission, and so on. And this will be the base for us to go further. So to conclude, what we already did. So I explained to you, we use already the electricity, we recycle our waste, we reuse the water, and mainly from the osmosis of the DI water. We manage waste with the chemical and the gases. We have a neutralization plant, we have scrubbers, and so on. What we do in the short terms will be to try to reduce, which is more circular, as we saw before, the 9 hours of potting, by a new spray tools, and also to reduce electricity. We'll make a major investment to replace the chillers and to upgrade the air conditioning systems. But very, very important is a master thesis doing which is doing Guillermo now, is on the flow analysis of our cleanroom, which will be a guide for us for the next actions. Give us a full picture, and with this, it will be a very important tool for us to decide. So, really to conclude everything. So, we have a cleanroom. We do science and technology and precision manufacturing in it. We have another environmental impact with electricity, water, the gases, everything we use. And we have some guides here with the 9 R's. And really what we can do now is to try to combine everything, this very complex equation, and try to make the minimal environmental impact. And really as a conclusion, so my word is obviously cleanrooms are and will always be intensive in natural resources. Adapt, you don't call your cleanroom green or sustainable, it is not. But definitely, as you can see, we explained you in the brief history of cleanrooms, that they are key for the miniaturization, for the precision manufacturing of the 20th century, and obviously of the time to come if you believe in the technology. So we definitely, as a citizen, as civil servant, have to make the optimum use of the cleanroom capabilities and perform the, we ask a researcher to perform the best and most useful science and technology inside. So as Harley Lehman here said, the present factor X in a comic, recommend you about circular economy, we are in excellent position to make the global sustainability transition a reality, as we have all the technological means we need to do so, and cleanroom may be part of it. The only question is a social question, is are we using them to build a sustainable future based on well-being or well-having? That's a question. So that's all I wanted to tell you. Just let me introduce you the next talk, which is June the 5th by Marek Gresak. I hope I pronounced well his name, on AI AD synthesis and characterization of plasmonic nanocrystals. And I would like to thank everybody, so the cleanroom staff and the direction here and the personnel at the Institute of Microelectronics Barcelona, because they really welcome this activity on sustainability we started 1 year ago, and really everybody is pushing in the right direction, I hope. I would like to thank also Guillermo Cito, the master thesis, and Anna and our tutors, Anna Petit et Laura Tenens from the ICTA here at the UAB, and all of you for your attention. Thank you.
Okay, thank you, David. Are there any questions for the audience? I think there is a questions and answers.
I cannot see it, so if you can ask the question.
Yeah, so you can either ask or right here in the question and answer, I can see it.
One question by Francesca.
No, yes, I was working.
Okay, David, you mentioned something about purchase. Could you please further comment on this? Well, with us, it's a huge topic, but just mentioning maybe what is more proper to us is about the tool. We definitely have to reflect on the tool purchasing because of CHIPS Act money. I mean, most of the cleanroom in Europe will be able to invest a lot of money in new tools, process tools I'm talking about. And well, maybe we would be better to refurbish, or well, if it's possible, if it's a refurbished tool, achieve your goals, or maybe if we could be able an old tool to give it to another institution, but still I think that you can really fit on the 9 hours from putting many things about the tool purchasing and refurbishing and so on. But now maybe the law, I don't know if it really the law is on our side, even if we have the do not harm significantly from the European Union advice. Is it really, it's not really easy, at least in Spain, to give a tool, a process tool to another institution and so on. So if something could be improved here, that would be great. And on purchasing, pues, many. Well, I'm thinking about process tool because that's what we are really busy with now. I hope it answers your question partly, or we can talk later about it. Thank you. So, don't know, Joan, if there is no more questions.
Yeah, we can I guess, close. So thank you everyone for attending the talk.
Yeah.
And next one will be, I think it's 5th of June, as presented by David. The next talk in the series on the Sustainable Nano Network.
Yes.
Okay, so good afternoon to everyone.
Yes.
And goodbye.
Bye.